We're going to talk today about a chapter 14 overview, and I'm going to start off with introducing this post-test area with a real-world problem. Microcontroller sound recording. So we've got a sound. If we want to record a sound, it goes through an AD converter, and it has some sort of sample conversion frequency there. And it goes into a microcontroller. And the sound is, of course, continuous in time. But when it gets into the A to D converter, it's converted into numbers, and I'll write them in hex. So it might be 6, 9, F, 2, A, and so on. And this is actually the core of something that's very, very commonly done in electrical engineering. When I was a graduate student, I had a friend whose name was Jim, who decided it'd be awfully funny to build a system just like this and record him farting. And he stored several different sounds in the microcontroller, and then he played it back, and it was very funny. And then he created a system that was inexpensive that would allow you to use it remotely. He created a company around it. He called it Jim's Machine, and he made quite a bit of money on it before it was usurped by another company overseas who were able to mass produce it for much less money. You can still buy them. There's still remote controlled fart machines out there. If you're curious, incidentally, about how this works in detail, take my digital signal processing course. And if you're curious about how to take an idea from an idea for an invention to actually a mass-produced commodity that can earn you money, take my Entrepreneurship for Engineering course. Let me talk about this analog to digital section, also called an A to D, a little bit more. So we have our sound, and our sound maybe starts to be low and gets to be pretty high frequency, and we're going to sample it. This is our X of T, and we're going to sample it with our sampling clock. And I'm trying to draw this roughly symmetrically. And so every time that the clock rises, we'll sample. And so our samples look like this. So from this, it's pretty clear that the low frequency portions are modeled well. If you were to reconstruct this, you get a pretty good representation of your original waveform, and so you'd hear it rather well. But as the frequency of your continuous time gets higher, it stops looking like what it should look like. It looks like a completely different waveform. It's even clearer if we take out that zero line. And this is a common problem in discrete time. So the problem, in just so many words, is that low frequencies sample fine, but high frequencies get aliased, which is the technical term for getting screwed up. So there are several solutions to this. Joe, can you give me one?
Increase the frequency at which you sample.
Yeah, exactly. So the first one is increase the sampling frequency. And if you increase it high enough, you solve the problem. The problem with increasing sampling frequency arbitrarily is that it also increases the amount of memory that you need to store your signals. It increases the processing power. So you both need to get a faster microcontroller, which costs more, but it also uses more energy. The faster you run these things, the more energy they use. And the other thing is that you're really not interested in all frequencies. So you're really not interested in frequencies greater than 20 kilohertz because you can't hear signals greater than 20 kilohertz. But yet, even if you've got a signal that's greater than 20 kilohertz, like was shown down here, it can still get aliased down into what looks like a much lower frequency. So we need a better solution. And the better solution is to remove the high frequencies that you don't care about. So in other words, we've got this sound, which is our X of t, and now it goes into our filter. So it's got some low and some high. Out of our filter, it only has the low part that you want. Now it goes into our A to D converter. And here's our sampling clock. And now this gives you what you want. So the goal of chapter 14 and the lab, we've got a lab coming up in this, is to build a filter just like this. And there's actually two sub-goals. The first is the easier one. Given a circuit, CKT is my abbreviation for a circuit. You're going to analyze its frequency characteristic. You're going to be able to tell me, given a circuit, is it a low pass? Is it a high pass filter? What's going on? And then separately, this is the harder one, but this second one is the one that you'll be actually paid to do. Given a set of frequency characteristics, you're told you need to build a low pass filter or a high pass filter. Design the circuit that does this. So this is the easy one that is in most undergraduate courses, and this is the more challenging one. I cannot tell you how rare it is for me to go through a year without hearing feedback from some cadet who's graduated saying that they've used the techniques in this particular section in graduate school or in industry. Most people simply don't know how to actually do the design phase. They only know how to do the analyze phase. And the reality is that in industry, nobody comes up to you with a circuit and tells you, someone else designed this, we don't know what it does, please tell us what it does. Instead, they come up to you with a problem and you say, hey, I can solve that using a low pass filter.